Hi, this is Math 2520, and this video is over section 8.6. And we're going to be looking at just integration strategies in general. And a lot of this is stuff we've seen, and we'll just go back over examples of each, but kind of how to make a game plan for integrating something that may look kind of difficult. So the first thing is look at whether you recognize what's being integrated as a antiderivative. It's something that you've seen. If it's, for instance, 1 over x, then you know, okay, that's the derivative of natural log of x. So you have that in mind. Or if it's some polynomial like x squared, there's ways of finding that. See if you recognize it first. Or if it's something like derivatives of arctangent or arcsine, or maybe just sine and tangent. The second thing is, can you do this with a basic substitution? Create like a u substitution and make the integral simple. If that's possible, then that's the first way to go, first way to try, I guess. All right, but we all know that not all integrals can be solved with a u substitution. Third is there any way to simplify the integrand, and it simples down to something that's easier? That may mean expanding the binomial, or finding a common denominator, or even dividing the polynomial down, or rewriting in sines and cosines. Then you'll look at, are there only higher powers of trig functions? So if that's the case, then you can look at what we did in previous section of this chapter, different trig strategies to solve it. Are there any radicals that have x squared or a squared, x squared minus a squared, x squared plus a squared, that kind of thing? Then we can use inverse trig substitution. Is the integrand a rational expression? Then it's possible to use partial fractions. Or you may have to use integration by parts. It's different possibilities, and you kind of go down this list to see, okay, does it fit any of these, and is that one I can try. Sometimes you have to use more than one method, sometimes you don't. Usually when you do use more than one method, one of these methods is some kind of substitution. And then if you're still stuck, then you may want to try again and just pick a different method to try, or a different way of going about it. Sometimes you don't always pick the best ways at the very beginning. And then the last ditch effort is think back and try to relate the integrand to another integrand you may have done in the class or in homework, or maybe even in an integration table. Alright, so we're going to go through examples. First example is just a basic antiderivative. This is a polynomial, so you just kind of reverse what we do for derivative. So instead of multiplying by the power and dropping the power by 1, we do the opposite. So when we take the derivative of this, we'll increase the power by 1 and then divide by that power. The antiderivative of this, and the antiderivative of 1 is just x. Right, and then we substitute, so simplify, so x cubed plus x squared plus x plus c. Pretty straightforward in that one. U substitution, we have x cosine of x squared dx. If we let u equal x squared, then du equals 2x dx. So x dx then equals du over 2. So we can rewrite the integral as 1/2 cosine of u du, and that's a much easier one that we can solve. So derivative of sine is cosine, so the antiderivative of cosine is sine. So we'll have sine 1/2 sine of u plus c, and then u is x squared, so it'll be 1/2 sine of x squared plus c. And if you reverse it, if you take the derivative of this, you'll get cosine of x, and then you'll get 2x out in front, and that those 2's will cancel, and you get x cosine of x squared. So you get what you're supposed to. This next one will be partial fractions. We have a linear term and a quadratic term in the denominator. So we'll set this up as 2x plus 3 equals x plus 1 over x squared plus 1, and that's going to equal a over x plus 1 plus bx plus c over x squared plus 1. Then you multiply by your common denominator, which is always the denominator of the original integral. And so when you multiply by that, you'll end up with, on the left, 2x plus 3. On the right, you have a x squared plus 1 plus x plus 1 times bx plus c. Okay, so now we distribute. So ax squared plus a plus bx squared plus cx plus bx plus c. And then we can kind of put like terms together. So a plus b x squared plus c plus b x plus a plus c. And so a plus b is going to equal 0 because there's no x squared term. C plus b has to equal 2 because there's the 2x plus 3, so it's 2x. And then a plus c has to equal 3. Alright, so we're going to get a couple things in terms of others. So a would equal a negative b, and so I can plug that into the last one, and I'll have negative b plus c equals 3. And so c would equal 3 plus b, and I can plug that into the second one, and we'll have 3 plus b equals 2. So 2b equals a negative 1, so b equals negative 1/2. And once you have b, you can get the rest. A then is 1/2, and c then is 5/2. Okay, now that we done that, we can rewrite this integral in terms of 3 different integrals. We'll have a being 1/2, so we'll have 1 over 2 x plus 1, and then b is negative 1/2, right? Yep. So we'll have negative 1/2 x plus 5/2 over x squared plus 1 and dx. so the first one, 1 over 2 x plus 1. Second one, we can split that up as well. Negative 1 over 2 x squared plus 1. And 5 over 2 x squared plus 1. And a dx, it's off to the side. Right. And then each of these, we'll have to find a different way to solve. So first one, that's just going to be 1/2 natural log of x plus 1. That's the easiest one. The second one, we're going to let that be a u substitution, where u equals x squared plus 1. And so this would become integral of -1 over, see if that's u, put u in the bottom, then du is, oh yeah, if that's u, then du is 2x. And so we don't have an x here. Should we have, oh, we should have an x. Oh, I forgot my x. Okay, that makes it more sense. So then x dx is du over 2. So we'll have a 4 on the bottom. Du, since I'm way over here, since du is 2x dx, we have x dx, we don't have the 2, so when we substitute in for x dx, we have to substitute in a 1/2 du, which puts another 2 in the bottom. And then the last one, that one we don't have an x on top, so we have to do this in a different way. It is x squared plus 1, which means think trig function, so it will be an inverse tangent of x. So this becomes 1/2 natural log of x plus 1, and then -1/4 natural log of u plus 5/2 inverse tangent of x. And then finalize it right down here, 1/2 natural log of x plus 1 minus 1/2 natural log on u was x squared plus 1 plus 5/2 inverse tangent of x. Right. The next type of strategy is integration by parts. This is when we have things multiplying. So partial fractions, when you have things to some kind of fraction involved. When you have things multiplying in an integrand, we can use integration by parts at times. So we let, here we'll let u equal x, so du equals dx, and dv equals e to the x dx, so v ends up being just e to the x. And so we write uv, so x e to the x minus the integral of v e to the x du, which is dx. And it gets an integral we can solve. This ends up being just e to the x plus c. And we saw earlier, if we have sines and cosines that have powers to them, we can use those. For this one, with sine being to a cube and cosine being squared, we're going to use a substitution where w equals cosine x, and dw equals negative sine x dx. Now we're going to take and hold back one sine of x, but the other sine squared x we're going to turn into 1 minus cosine x. Remember, sine squared plus cosine squared is 1. Alright, so this we're going to turn a sine squared into 1 minus cosine squared x. Then we're going to have a sine x and a cosine squared x dx. And then we let w equal cosine x. So wherever there's a cosine, we put w. If it's squared, then w squared. So 1 minus w squared. And then we'll have a w squared on the outside. And then this sine x and this dx is our dw. We'll want to make it negative, since there's a negative sign. Alright, so we can simplify this. So it'd be w squared plus 1 times w squared dw, and then further simplify. Sorry, that should be a minus 1. W to the 4th minus w squared dw. And then these we can take the integral pretty easily. W to the 5th over 5 minus w to the third over 3 plus c. And then resubstitute in what we have for w is cosine x. Cosine to the 5th over 5 minus cosine to the 3rd over 3. And the other thing we looked at is inverse trig substitution. So here with x squared on the bottom and plus 1, and there's a square root there, we'll use x equals tangent theta. So this becomes the integral of 1 over square root of tangent squared x plus 1. And that tangent squared x is secant squared theta. Let me make this theta. And then the top, since we're letting tangent be, actually, hold on, let me redo this for a second here, make it more clear. I should have did this in the first step. So if x is tangent theta, then dx is secant squared theta d theta. That should be on top. Okay. Then we can make the bottom secant squared theta. Top still stays secant squared theta d theta. And so bottom then becomes, when you take the square root of squared, you get just secant theta. And then this becomes just the integral of secant theta without any square. Right. We solved this once. I'm going to do it again though, because I know we've used it once too where we didn't solve it again, but I want to do it again just out of practice. We can make the secant theta plus tangent theta over secant theta plus tangent theta. So I'm just multiplying by 1. And we're going to let u equal secant theta plus tangent theta. So du equals secant squared theta plus secant theta tangent theta d theta. Now, going back to our integral, I want to do one simplification before we do the actual substitution here. I'm going to distribute that secant. So I have secant squared theta plus secant theta tangent theta d theta over secant theta plus tangent theta. Okay. So now we can do the substitution. The top is the same thing here. So we have a du. The bottom is what we have for our u. So it boils down to a pretty straightforward integration. And then we let u back equal back what we set it to. So this is the natural log of secant theta plus tangent theta plus c. These are the absolute value signs when you integrate should always have absolute values. I'm sorry, the natural log sign should always have absolute value signs. And then actually we won't go even farther back. Our integration was that x equals tangent theta. So we have to kind of bring that into it. That means that the x equals tangent theta, then our secant theta will equal the square root of x squared plus 1. And we can get that from a triangle here. Whereas this is going to be x. This is going to be 1. So this is the square root of x squared plus 1. So tangent is x over your sine, opposite over your adjacent, so it's x over 1, which is x. And secant is r over adjacent. So we bring this back to x's. So square root of x squared plus 1 plus x plus c. So similarly, if we look at integrations that have square roots of like 1 minus x squared, we can use an arc sine and recognize this as the derivative of arc sine. So 1 over square root of 1 minus x squared is the derivative of inverse sine of x. Okay, we had something similar up here. What is it? Where I went from here to here. That's because the derivative 1 over x squared plus 1 is inverse tangent derivative. So a similar idea here as well. And so the integral then equals inverse sine of x plus c. And just recognizing some of these. Then it goes on as bad as we think when we know all the information behind it. When you have exponential functions, something like e to the 2x sine 3e to the 2x dx. Here I will want to do a u substitution at the first. I'll let u equal e to the 2x. So du equals 2e to the 2x dx. And so I have du over 2 is e to the 2x dx. And so this integral becomes 1/2 sine of 3u, which I remember if I want to include that 3 or not, and then du. And so the antiderivative of sine is negative cosine, so we have negative 1/2 cosine of 3u But if we do this, we'll end up with the 3/2 out, so we have to divide by 3 as well here, and plus c. So negative 1/6 cosine of 3u plus c. Right. So with these, you may want to try them first to see the best way of going about it, and if you can, don't spin your wheels. I'll give you some clue if you want to do that, and you want to pause this video and try it first. For the first one, look for a u substitution. Second one, you can also do this with a u substitution. Third is obviously powers of trig. And then the last, what's it called? Integration by parts. I have partial fractions on my mind. I'm like, that's not the way of doing it, but what's that called? Alright, so you want to try it, pause the video, go try it. Alright, so now I'm going to go through the solutions. So the first one, I'm going to do a u substitution. That would be 2x to the third minus 3x squared plus 2. So du equals 6x squared minus 6x dx. And then I'm going to divide over 6. So I have du over 6 equaling x squared minus x dx. That's what I have on top. Right, so I can make this integral now 1/6 and then a du, and then on the bottom it's just 1 over u. And so this becomes 1/6 the natural log of u plus c. And then this becomes 1/6 natural log 2x cubed minus 3x squared plus 2 plus c. Similar idea here, do a u substitution. I know it looks like a inverse trig substitution. You could probably do that and get away with it. But why do something harder when a u substitution is kind of straightforward? So we can let u equal 1 minus x squared, so du equals negative 2x dx. So du over 2 equals negative, we'll do it this way, make that positive, x dx. So we can substitute this in now, or negative 1/2 square root of u du. I'll rewrite this, negative 1/2 u to the negative 1/2 du. And when I do this, is just applying a power rule now. So we add 1 to the power, and then divide by it. So it'll be u to the 1/2. And we divide by 1/2, so we're going to multiply by 2. And it'll be plus c there. So those two's cancel. We get minus square root of u plus c. And then that will be minus square root 1 minus x squared plus c. So with powers of trig, we're going to leave one cosine to the side and use cosine to the 4th. and let this become sine cubed 1 minus sine squared x. So that's your cosine squared, but then we're going to square it so it's to the fourth. And then cosine x dx. Then we're going to let w equal sine x. So dw is cosine x dx. So this integral now becomes w cubed times 1 minus w squared, and then cosine dx is just dw. Alright, so we'll FOIL this out now. So 1 minus w squared, and then we're squaring that, so we'll have 1 minus 2w squared plus w to the fourth. dw. And then we can multiply the w cubed in. So w cubed minus 2w to the fifth plus w to the seventh dw. And these are just the power rule. W to the fourth over 4 minus 2w to the sixth over 6 plus w to the eighth over 8 plus c. And then just simplify the 1 in the middle. And then the last step, bring in the w as sine of x. And there you go. Sine to the fourth over 4 minus sine to the sixth over 3 plus sine to 8 over 8 plus c. And then the last one on this page, we'll use integration by parts. We're going to let u equal x, so du equals dx. And then actually before we do that, I want to adjust this integral sum. So cosecant is 1 over sine, and cotangent is cosine over sine, so I'm going to make this cosine x over sine squared x dx. And so then dv is cosine x over sine squared x dx. And so v is going to be negative 1 over sine of x. And so we can write this now. Negative bu v, so x over sine of x uv minus integral of a negative 1 over sine x dx. And so this is negative x over sine x plus the integral of cosecant x dx. And then integral of cosecant x is natural log of cosecant x plus cotangent x. Oops. Plus c. All right. Now, a couple interesting substitutions here. Here we have natural log of x dx over x square root of 1 plus natural log of x. We're going to let u equal natural log of x squared. So du equals 2 natural log of x times with the chain rule, 1 over x dx. So 1/2 of du equals natural log of x over x dx, which is what we have here. So this then becomes 1 over 2 and du, and then inside the square root we'll have 1 plus u. I can rewrite this 1/2 1 plus u to the negative 1/2 power du. And so when we take the integral of this, we'll get 1 plus u to the 1/2 power, and then we gotta divide by that 1/2, so we'll multiply it by 2 and plus c. So the 2's cancel, you get 1 plus u to the 1/2 power plus c. And then u is natural log of x squared, so we'll get square root of 1 plus the natural log of x squared and plus c. The last one here, e to the x plus e to the x. It's hard to say. E to the power of x plus e to the x. We're going to separate this. So I have e to the x and e to the x. Because the powers are adding them, the two are multiplying. And then we're going to let u equal e to the x and du equal e to the x dx. And so we can simplify this as this e to the x dx is du. And so that would be e to the u du. When we integrate this, we get e to the u plus c. And e to the u is e to the x plus c. Very unique one. Alright. We'll look at some other integration methods in the next section. I'll see you then.